Good morning everyone. My name is Dhanush Kumar and my registration number is 22MIA1104. Today I will be presenting on the ID algorithm, a well-known encryption technique used in network security. I will explain its history, internal structure, mathematical foundation, working process, application, and significance in modern cryptography. Introduction to network security. Network security ensures the confidentiality, integrity, and availability of information. Cryptographic algorithms help prevent unauthorized access and protect data during transmission. One such algorithm is IDEA, International Data Encryption Algorithm, which has played an important role in securing communication systems, especially in earlier cryptographic tools like PGP. In this presentation, we will explore how IDEA, which is an international data encryption algorithm, enhances security in network security. History of IDEA algorithm. IDEA was created in 1991 by James Massey and Exu Lake. Initially, it was called IPES, Improved Proposed Encryption Standard, and was intended to replace the older DES algorithm. After further development, it was renamed IDEA algorithm. The algorithm became widely recognized when it was used in PGP, which is pretty good privacy, which was a globally used secure email encryption system. Despite being patented earlier, IDEA became highly respected for its security strength. What is IDEA algorithm? IDEA is a symmetric key block cipher. This means it uses the same key for both encryption and decryption. It works with a 128-bit key and encrypts data in 64-bit blocks. Its security mainly comes from combining three operations: XOR, modular addition, and modular multiplication. This combination provides excellent resistance against cryptographic analysis and makes IDEA algorithm highly secure. Mathematical foundation. The mathematical strength of IDEA comes from using operations from different algebraic groups. XOR. XOR works on binary fields. Addition. Addition works modulo 2 power 16 and multiplication works modulo 2 power 16 plus 1. These operations behave differently and are hard to analyze together. Because of this diversity, attackers find it very difficult to detect patterns or predict keys, making IDEA extremely robust. IDEA block structure. IDEA works on 64-bit blocks of data. Each block is divided into four 16-bit subblocks. The algorithm processes these blocks through 8 identical rounds, followed by a final output transformation. Each round performs a series of mixing operations on the subblocks. This helps spread the influence of each bit across the output, improving security. Key schedule of IDEA algorithm. Although IDEA uses a 128-bit main key, the encryption process requires 52-bit subkeys. These subkeys are created by rotating and extracting bits from the main key. For each of the 8 rounds, 6 subkeys are used. The remaining 4 subkeys are used in the final transformation. This key schedule ensures that even a single bit change in the original key produces dramatically different subkeys, which shows the avalanche effect. IDEA round operations. Each round in IDEA uses 3 operations: XOR, modular addition, and modular multiplication. XOR. XOR provides bit level scrambling. Second, addition mixes values arithmetically, and multiplication introduces non-linearity. Again I repeat, XOR provides bit level scrambling, addition mixes values arithmetically, and multiplication introduces non-linearity. When these operations are combined, they produce strong confusion and diffusion that are essential in encryption. Encryption process. During encryption, plain text enters the first round where it is mixed with subkeys using the 3 core operations, which is XOR, addition, and multiplication, as we've seen in the previous slide. This process continues through all 8 rounds. After the rounds are completed, a final output transformation is applied, producing ciphertext. The output appears completely random and unrelated to the original message, ensuring confidentiality. I again explain this PPT, this slide, because it's very important. The encryption process. During encryption, plain text enters the first round where it is mixed with subkeys using the 3 core operations which we saw in the previous slide, like XOR, addition, and multiplication. This process continues through all 8 rounds. After the rounds are completed, a final output transformation is applied, producing ciphertext. The output appears completely random and unrelated to the original message, ensuring confidentiality. Let us see the decryption process. Decryption is as similar as the encryption. Decryption in IDEA simply reverses the encryption process. The same subkeys are used but in the opposite order. I repeat, the same subkeys are used but in the opposite order. Inverse operations for addition and multiplication are applied. This reversibility ensures that the ciphertext can be perfectly transformed back into the original plaintext as long as the correct key is used. As we use the correct key, it surely ensures that ciphertext can be perfectly transformed back to the original plaintext. Next, we see security strength of IDEA algorithm. One of the biggest strengths of IDEA is its resistance to cryptanalysis. For more than 30 years, no practical attack has been broken the full 8-round ID algorithm. Only reduced versions such as 3 or 4 rounds have been studied or partially broken. No one can break this algorithm after 3 or 4 rounds. The full 128-bit key strength remains secure even today, demonstrating its excellent design. Comparison with AES. Although idea was strong, AES eventually became the global standard. AES uses 128-bit block size and supports 128, 192 and 256-bit keys. It is faster, more efficient on modern hardware and approved internationally. While AES is widely used today, IDEA remains historically important and is still found in legacy systems. Application of IDEA algorithm. IDEA was mainly used in PGP, which secured email and files. It is also used in older file encryption tools, secure communication systems, and some VPN technologies. Many older banking systems and embedded devices also implemented IDEA due to its computational efficiency. Real-world use cases. Some real-world examples include secure email applications, yearly VPN encryption, legacy communication equipment, and certain embedded hardware tools. In academic circles, IDEA algorithm is still used for research and teaching due to its elegant design. IDEA in modern times. Today, IDEA is less widely used mainly due to patent restriction in the past and the rise of AES algorithm. However, it remains present in legacy systems and continues to influence modern cryptographic algorithm design. Its mathematical structure is still studied in universities and research institutions. Advantages and limitations. The key advantages of IDEA include strong security, efficient software performance, and resistance to major attack techniques. On the other hand, its limitations include earlier patent issues and the fact that AES has become the preferred standard. Despite these limitations, IDEA remains one of the strongest classical encryption algorithms. Summary of how IDEA works. To summarize, IDEA uses 8 rounds of operation based on XOR, addition, and multiplication. It uses 52 subkeys derived from one 128-bit key. These operations collectively scramble the input data until the output becomes highly unpredictable. This structure makes IDEA very secure and reliable. Let's go through the algorithm once again for your reference. And the final part, conclusion. In conclusion, IDEAs played a major role in shaping modern encryption. Its combination of mathematical operations, strong design, and long-term resilience highlights why it remains a respected algorithm. Understanding IDEA provides a strong foundation for exploring more advanced modern cryptographic methods. Thank you for listening.